Good morning, Pirates. Today we're going to talk about some advanced calorimetry problems. So let's just say if you look at this samples here, we start with a piece of aluminum that has a mass of 26.97 grams. And let's say we place that piece of aluminum into a beaker of boiling water and we let it sit for 5 minutes. Now remember, water boils around 100 degrees Celsius. While that is boiling, we fill up a styrofoam cup with 50 grams of water and it's at room temperature, 20 degrees Celsius. After the aluminum is heating up in this boiling water for 5 minutes, we take that piece of aluminum pretty quickly and we remove it from the hot water and drop it into the styrofoam cup. So here you should see we have the hot piece of aluminum plus the 20-degree water. Think about what's going to happen over time. The hot aluminum is going to give its energy to the cold water. Over time, the aluminum that was originally at 100 degrees Celsius, since it was in the same boiling water, is going to give up some of that energy to the cooler water. So you can imagine the hot aluminum is going to cool down and the 20-degree water is going to start to heat up. What you also need to know is over time, the final temperature that this styrofoam cup full of water and aluminum reaches is 28 degrees Celsius. So let's talk about how this works. Obviously, the aluminum is giving up its heat and the water is absorbing it. And it's also, understandably so, that the amount is the same. So if the aluminum is losing 100 calories, then the water is absorbing or gaining those 100 calories. So we can use this concept. Heat loss equals heat gained. Unfortunately, though, the same amount of heat gained and lost, the amount, the numerical part, is exactly the same. However, they're in opposite directions. So we need to add this negative sign to account for the mathematical heat change. So let's try doing a problem like this. If we look at our equation from before, if we want to solve for Q, or heat, we know it's the mass times the specific heat times the temperature change. However, in this case now, we know the heat lost by aluminum is going to equal the negative amount of the heat gained by the cooler water, or Q lost equals negative Q gained, or if we actually plug in our Q equation down here, we get MC times temperature final minus temperature initial lost for aluminum in green here is equal to the negative mass times specific heat times the temperature change here for the styrofoam cup of water. Before we can even try this, we have to start thinking about our data, and I find it very helpful to make a data table when you have advanced calorimetry type problems. So in black, we're going to write all of our data for the water. And the water we're referring to is not the boiling water up here. The only reason we use this boiling water was to heat up the aluminum. We're talking about this scenario here, which is the styrofoam cup of 50 grams of water at 20 degrees Celsius. So down here, mass of water that we're starting with is 50 grams. The initial temperature is 20 degrees Celsius. Specific heat capacity of water is 1 calorie per gram degree Celsius. And the final temperature of the water, the final temperature, this 28 degrees, is going to be for both the water and aluminum, because both of them are sitting right inside that styrofoam cup if you look closely. And over time, eventually, as aluminum gives some of its heat energy to water and water absorbs it, they're both going to reach that 28 degrees Celsius, and that's where it stayed. So final temperature for water is 28 degrees Celsius. And the final temperature down here for aluminum is also 28 degrees Celsius. Okay, now let's look at just the aluminum. At the very beginning here, we put aluminum on the balance and we saw the mass was 26.97 grams. The specific heat capacity is what we are solving for. And then the initial temperature of the aluminum, remember for 5 minutes it was sitting here in this boiling, this beaker of boiling water. So that's at 100 degrees Celsius. All right, now we can actually solve for our unknown, which is the specific heat capacity of aluminum. So if we look at our equation up here, we can plug it in down below. So if we set the amount of heat lost by aluminum, the mass times specific heat times T final minus T initial, if we set all that equal to the negative amount of the water, mass times specific heat times temperature change, T final minus T initial, gained. So remember, the cool temperature of the water, the styrofoam cup is gaining some of that heat energy that aluminum is losing. Okay, so if we plug in our information here for aluminum, the mass was 26.97. The specific heat, remember the C value for aluminum is what we're looking for. So I'm going to call that X, since that's what you're comfortable with in math. Now the temperature change, remember you have to stay consistent. You always have to do final minus initial. It's not always the larger minus the smaller number. So the final temperature of aluminum is 28 degrees minus 100. So you can already see we're going to have a negative answer on that side. Now if we switch over to the side for water, the mass of the water up here was 50 grams. Once again, don't forget that negative symbol. Times the specific heat for water is 1. This is all up here in the data table. And then the temperature change. So the final temperature for both substances was 28 degrees Celsius minus the initial temperature of the water in the styrofoam cup was 20 degrees Celsius. Okay, so I'm going to simplify this a little bit more. So on the left side, we have 26.97 times X times, if you take 28 minus 100, we have negative 72. And then on the right side, we have negative 50 times 1, so that's 50, times 28 minus 20, which we know is 8 degree change. So let's keep going. On the left side, we're going to take 26.97 in your calculator times negative 72. So we get negative 1,941.84 times X equals, we take 50 times 8, we have negative 400. So mathematically here, you could see that on the left side, the X right now is being multiplied by negative 1,941.84. The only way to cancel that number is if we were to divide both sides by that number. This number would cancel to 1, or just X. And we have to do the same thing to both sides. So now if we take 400 divided by 1,941.84, we get X equals 0.205. So I'm going to round it up to 2, 1. One thing I should point out here is, if you notice, we're dividing a negative by a negative, so it cancels to a positive. And this is our X value, 0.21. So if you remember up here, we were solving for the specific heat capacity of aluminum, which is in calories per gram degree Celsius. And that is how you do advanced calorimetry. Have a great day.